real gases. So in an ideal gas, there are no attractions between gas particles. When they bump into each other, they collide elastically and they don't interact with each other. They also have negligible particle volume. But real gases do have attractions and they do have volume. What we see is that real gases act like ideal gases at STP, standard temperature and pressure. And here's a table comparing the molar volumes of an ideal gas, this is what you would calculate the molar volume to be at STP, to some actual gases and their actual volumes. And you'll see that they are very close to an ideal gas. In fact, helium nails it, 22.41. At least to 4 significant figures, it's behaving exactly like an ideal gas. What happens, though, is at high pressures or low temperatures, we see that they do not behave as ideal gases. As we take argon, which had a molar volume nearly identical to that of an ideal gas, that was right here, argon, no, it's not on there. Anyway, it is. If we compress that, what happens now as the pressure gets higher and higher, there's less and less empty space, and now the size, the volume of the actual particles isn't negligible anymore. It becomes a factor. Because if you squish those together even more, you would eventually cause them to be touching each other. They would condense into a liquid, and now they're not a gas anymore. The ideal gas, at having no volume of particles, as you compress it and compress it and compress it, eventually you're just going to get to zero volume because there aren't really any particles there. So what happens is, with the real gas, the actual volume is greater than what's predicted by the ideal gas law. So here we see a graph of molar volume versus pressure for an ideal gas in the red and argon in the green. And so what we see is they behave the same over here at lower pressures. These are incredibly high pressures, by the way. 200 atmospheres, that's a lot of pressure. So we increase the pressure, we're squeezing the argon molecules, atoms, much closer together, and now the size, their volume has an effect. And so we see a larger molar volume than predicted by the ideal gas equation. Well, if you're dealing with gases at super high pressures, you might want to be able to calculate, well, exactly how is it different, because that could be important. So 1873, a guy named van der Waals modified the ideal gas equation. So here's the ideal gas equation predicting the volume of a gas. He added a term. So it's volume equals nRT over P plus N, still the moles of the gas, times a fudge factor, basically. It's called the van der Waals constant. It's going to be different for each different gas because the volumes of the different particles, the molecules, are different. And so this increases the volume and helps us to predict the real volume. At high temperatures, if we look at the predicted pressure of a gas, it's nearly identical to that of an ideal gas. But at low temperatures, the pressure is less than what we would expect. And this is because at low temperatures, gas atoms spend more time interacting with each other. So this isn't the greatest analogy, but it's the only one I can come up with. Oh, actually, there's two of them. Velcro or relationships? Velcro? Okay. So you've got two people covered with Velcro suits, right?
In a relationship?
They could be in a relationship, but we're going to leave that one on the side. So if they run into each other, run past each other, really, are they going to stick? That's the question. There's going to be a bit of resistance, right? If they're moving very slowly and they just kind of come up to each other and bump shoulders, they're probably going to get stuck to each other. If they're running past each other and just graze each other, they're probably not going to get stuck. right? Less time interacting. I'm actually not liking the Velcro one. We're going to go to the relationship. So you've got a single guy, single woman. Maybe they're on the sidewalk in New York City, and they're walking in opposite directions, and they bump into each other. But they're just like on a mission. I'm walking, and they bump into each other. Do they fall in love and get married? No. Why not? They didn't interact, Hollywood. Right? It's not Hollywood. What if they're at a party and they're hanging out with each other and there's not too many other people to talk to and they're spending a lot of time with each other? Now the chances of them getting involved with each other is greater, right? Because they're interacting more, they're spending more time with each other. I didn't really like that one either. Oh well. Hopefully you get the idea though. When the gap.
Party and you put them in Velcro suits, it would have been better.
Maybe I'll have to look. I'll work on that one in my spare time, which I don't have any of. So gas particles. I think if we think about this, it will make sense. So when the particles are moving rapidly, they're bouncing off of each other. There's not really any time for any interaction to take place. As they slow down at lower temperatures and they're moving more slowly, now when they bump into each other, forces of attraction can have an effect. They're still going to bounce off of each other. They're not going to stick to each other indefinitely. But they will interact, and that will cause them to slow down even further. It's going to make the actual pressure less, because some of the time that they would have been bouncing into the walls, they're now pausing when they're bouncing off of each other. And see, that's wrong. So van der Waals also modified the ideal gas equation to take this into account, the effect of intermolecular attractions. It makes the pressure smaller, so we're subtracting van der Waals constant times the quantity moles of gas divided by volume squared. So that makes the pressure less. If you combine those two, you get this mess, which is known as the van der Waals equation. And happily for you, we're not really going to do anything with it. I just want you to know, I've introduced you. Class, here's the van der Waals equation. Van der Waals equation, here's my class. You've been introduced. Right? If we need to do more precise calculations, or if we're working at low temperatures or high pressures, or heaven forbid both, we need to use the van der Waals equation. Those constants, A and B, you'd look up. So, here's a table and it gives the units and everything, and you could plug those into the equation and figure out what the actual volume or pressure or temperature was that you were calculating. So here's a graph where we've taken pressure times volume over gas constant times temperature. So PV over RT, that's equal to N, right? Number of moles. So for an ideal gas, as we increase the pressure, we would see that it stays the same. It's 1. For a gas like helium, as we increase the pressure, we see that this increases. And that's telling us that the most important factor for helium is the volume of the particles. So as we increase, the number gets larger, so that means that the molecular volume is more important. For gases like water or for xenon, up to a point, N is less, and that tells us that for these gases, the intermolecular attractions are what's more important. And they cause it appears like there's less gas than there actually is.